So today's lesson is going to be on thermodynamics, and we're going to do some introductory material. So a quick review. Heat is the energy, and we measure that in the units of joules. And temperature is defined as the average kinetic energy of molecules within a system. And we know that the Kelvin scale is used to show us the absolute temperature, where at 0 Kelvin, that's the lowest possible temperature before there's no energy left in a system, meaning kinetic energy is 0. All right, so we know particles are constantly moving. At some point, if we adjust the temperature low enough, those particles slow down and get slower and slower. All right, so at 0 Kelvin is where there's no energy left. We know that kinetic energy is directly related to the temperature of a substance. We've also talked about the difference between a system and the surroundings. The system is the actual chemical reaction, whereas the surroundings is everything else. So we've looked at heating and cooling curves. So if we were to look at this heating curve here, just because we add heat to a system does not mean temperature increases, and this happens at phase changes. All right, so right here and right here, we are adding heat. All right, yes, our heat is being added, but the temperature is remaining 100 degrees Celsius. So we're going from a liquid to a gas. So that heat that we're adding is being used in order to separate our particles and put them from the liquid phase into the gaseous phase. And we know that heat specifically is breaking those intermolecular forces. And so at this point, we say substances have potential energy because we know that gas particles are really far apart. Liquid particles are a little bit closer together. And our solids are very close together. So if we are to change the spacing of a particle, meaning going from a solid where they're close together to a liquid where they're a little bit further apart, solid to a liquid, we are changing the potential energy. The potential energy is decreasing as I go from a solid to a liquid because these particles have less room to expand as they have already expanded some. And the same thing when I go from a liquid to a gas. My potential energy decreases again because at my gaseous phase, my particles are already as far apart as they can be. We can look at temperature in terms of kinetic energy. So we know that kinetic or temperature is the measure of the average kinetic energy. So some particles are moving slower, some are moving faster, but overall it is the average. All right, and we've looked at this Maxwell-Boltzmann distribution curve before. If this line right here is my activation energy, the energy needed to get a reaction started. All right, at a high temperature, I have more particles that are above that activation energy than I do below the activation energy. And if we were to look at it in terms of a cold gas, I don't have as many particles above that activation energy. So kinetic energy directly related to the temperature. So let's look at our first law of thermodynamics. Energy can neither be created or destroyed, but it can transform from one form to another. So our energy is able to change forms and is going to do so during a chemical reaction. It can do so during a phase change because we are using that heat energy to change the potential energy, for example. It can change the temperature, all right? And this is going to ultimately result in energy being transferred either into or out of the system, and it will be transferred in the form of either heat or through work. So delta E is our change in both the potential and kinetic energy of particles. All right, remember, potential energy is their spacing, kinetic energy is their movement. So two different types of energy. Our Q is the heat transferred into or out of the system, and we've looked at Q before. All right, so if Q is going into the system, we make it a positive value, and if it's going out of the system, then we make it a negative. So if the reaction absorbs heat, it's positive. If it releases heat, it's negative. So here's our new concept, and this is work. So work can be done on a system by the surroundings. And if energy flows into the system, then it is a positive W value. And when energy flows into the system, the surrounding does work on the system. If my work is a negative value, in this case, energy is flowing into the surroundings from the system. So the surroundings are getting energy from the reaction. So the system itself is doing work on the surroundings, and our work would be a negative value. If we were to look at the formula for work equals force times distance. So work is going to result in a change in the volume of the gas, okay? Because those particles can be moving their distance here, closer together, further apart. And so let's investigate this. So potential energy is stored energy, whereas kinetic energy is the energy of motion. So when we have our bicyclist here, our bicyclist is at the highest point. All right, so potential energy is mgh, the mass of the object times gravity, 9.8 meters per second squared, times the height. So height in this case is how far the bicyclist is from the ground. So at his highest point, he's as far from the ground as he can be, so he has the highest potential energy. All right, and this potential energy can be related to our spacing of particles, where the further the spacing of particles are, or the closer those spacing of particles are, all right, that is the height, all right? However, as the bicyclist moves closer to the ground, so as the bicyclist moves down to the ground, he's getting closer to the ground. So his potential energy is decreasing because he's making it closer to the ground. Gravity is taking a hold of this bicyclist as he falls down to the ground, and we can look at kinetic energy. Kinetic energy is 1/2 mv squared, where m is the mass of the object and v is their velocity squared. All right, and velocity is just a big fancy term for speed. So as the bicyclist falls down to the ground, his speed increases. Because his speed increases, so does kinetic energy. So let's look at an endothermic process, and we do have this graph that we've seen a bunch of times. All right, our reaction coordinate graph over here in terms of the potential energy. So in this case, my products have more potential energy than my reactants, okay? So their potential energy is higher. Now, if the products have less kinetic energy than the reactants, kinetic energy is related to temperature. That means the products also would have a lower temperature. All right, so our heat is moving from the surroundings into the reaction itself. The endothermic reaction is absorbing the heat from the surroundings around it. So we know that work can cause a change in pressure. So here we have an example with a piston. All right, so the gas is doing work on the piston. All right, the gas outside. So we have gas outside and we have the gas inside. Okay, so we have the gas on the outside, the surroundings. We have the gas on the inside, the system. So in this case, the energy is moving from the gas to the pistons, and the pressure outside of this container is greater than the pressure inside. So if the pressure outside is greater than the pressure inside, what is happening? Pushing down is a greater pressure, so we see a decrease in volume. So in an exothermic process, we've already learned that the products have less potential energy than the reactants. Now, if the kinetic energy of the products is greater than that of the reactants, that means they also have a higher temperature, because kinetic energy is related to the temperature, right? Temperature is the average kinetic energy. So in this case, heat is moving from the system, the reaction itself, and it is going to the surroundings. And this will happen until equilibrium, thermal equilibrium, is established, meaning we have a rate transfer that is the same. So in this case, what we have here is our pressure is being caused by the particles of the piston on the inside being greater than that on the outside. So the inside is greater pressure than the outside, meaning the inside, basically think about it, pressure pushing up, causing an increase in volume. So when we have a change in energy that is positive, the internal energy of the system increases. A negative overall energy means a decrease in the system. Now, it's important to remember here and to think about this. Q and W don't always have to be positive or have to be negative. We need to think about change in energy in terms of what is happening. Okay, so if Q is positive and work is positive, delta E, the change in energy, equals Q plus W. So a positive plus a positive will give me an overall positive delta E. If Q is positive and work is negative, so I have a positive plus a negative. If this Q value is greater than the W value, overall I would have a positive E. If the W value is larger than the Q value, I would have a negative E. So E will depend on the magnitude of Q and W. So we have to look at it, which one is larger. If I have a negative for both, a negative plus a negative is an overall negative. And then again, if I have a negative and a positive, it is going to, again, depend on the magnitude, all right? So if my Q is negative and my W is positive, a larger W than the Q will give me an overall positive E. A larger negative Q would give me a negative. So again, our change in energy is depending on that magnitude of the Q and the W. So let's do some practice here. A system does 975 kilojoules of work on its surroundings, while at the same time absorbs 625 kilojoules of heat. So what is our change in energy? All right, it tells us that the system is doing work on the surroundings. And it tells us that we are absorbing heat. So absorbing heat is endothermic. Therefore, our Q is positive. Remember that from honors chemistry. All right, positive and negative just tell us if heat has been released or absorbed. Because the system is doing work on the surroundings, then my W is a negative. All right, so remember, a negative means the system does work on the surroundings. So my change in energy is Q plus W. So now I'm just plugging in my values, my positive 625 and my negative 975. And so overall, I end up with 350 kilojoules, and that is a negative value. So overall, I have a negative change in energy. So let's do this practice problem. You can pause the video and then come back to it and check your work. All right, so the system is doing 455 kilojoules of work. I'm sorry, the surrounding is doing 455 kilojoules of work on the system. So that is a positive W. So that is a positive 455. The system releases 253 kilojoules of heat. So that is a negative Q. So what you're noticing here is just because the system is releasing heat doesn't mean that it is going to, the surroundings are not still doing work on the system, or they are doing work on the system. It can go both ways. We have to look at the magnitude of each, right? Because in this example above here, we had a positive Q and a negative W. All right, so here we have a positive W and a negative Q. So when you put those together, you get 202. And that is in kilojoules. All right, so let's derive the equation for work. Pressure is force divided by area. So I can rearrange the equation so where force is pressure times area. And the change in volume is the area times the change in distance. So I can rearrange this to where the change in distance is the volume divided by the area, and that's the change in volume. So we've already seen work equals force times distance. So force is pressure times area. Distance is volume divided by area. So here I am. We're just substituting in. All right. If area is on the top and the bottom, it cancels, leaving me with pressure times change in volume. So work is pressure times change in volume. Now, we're going to put a negative in front in order to give work the correct sign. Okay, so it'll be a negative P times delta V. So a gas expands from 0.79 liters to 2.3 liters in the cylinder under an external pressure of 1.05 atmospheres. Calculate the work associated with this expansion of a gas. So we've just determined that work equals negative P times delta V, where delta V is the change in volume. And remember from honors chemistry, change in volume is final minus initial. So my pressure is 1.05. My volume is my change, final minus initial, all right, which goes in there. So negative 1.05 atmospheres times 2.3 minus 0.79 liters, and this gives me a work of negative 1.59 liters per atmosphere. So what does this tell us? I have a negative W. So that tells me that the system is doing work on the surroundings. Now, let's take this a step further. We can get rid of our atmospheres and find just the joules because work is measured in joules. So to get it into joules, we're going to use this conversion factor, 101.3 joules divided by 1 liter per atmosphere. All right, so my liter and my atmosphere now cancel out, giving me my overall work. All right, and in this case, it is now just in joules. Work is measured in joules. So this tells me my system is exothermic and the system is expanding into the surroundings, which makes sense because the system is doing work on the surroundings.